Hello viewers, our names are Jamie He, Lyndon Sher, Emmy Tong, and Jackie Shu, and we have created a physics experiment geared towards high school students, which we aimed for to be easily accessible. Our experiment will allow students to learn about harmonics, standing waves, and resonance line width. It will also allow students to gain experience with Fourier transforms. Firstly, let's explain standing waves. Standing waves are created when a wave reflects off a boundary and interferes with the original wave. The wave looks like it is stationary, hence the name. A standing wave has points called nodes, which do not move, and antinodes, which experience the most movement. The distance between two consecutive nodes is half the wavelength of the standing wave. Standing waves can exist on strings, which we investigate in this lab, and also in tubes of air. Then, let's cover harmonics. The simplest and most common standing wave is the fundamental frequency, where only one antinode is present in the wave. This is also the lowest frequency at which the object can vibrate, but it doesn't stop there. If nodes are added such that the string is divided into equal portions, harmonics can be emphasized. Here is the first harmonic, the second harmonic, the third, etc. On a string instrument, nodes are added by lightly touching the string at a certain point. Harmonics are a type of overtone, higher frequencies that are always present when a note is played on an instrument. The average overtone has a frequency that is not an integer multiple of the fundamental frequency, unlike harmonics. Overtones aren't typically discernible to the human ear because they are so quiet, but they give each sound its unique quality, known as timbre in the musical world. However, not all waves are sinusoidal, such as all of these waves currently being shown on screen. How then would we graph them with functions and work with them? The answer to that is Fourier transforms.
Any continuous periodic function can be represented by adding an infinite amount of sine waves together. On screen is a function that is the sum of three sine waves, represented by capital A, B, and C. Here you see the functions for each sine wave. Each lowercase a represents the amplitude of its respective wave, and if you change the amplitude, the original function changes accordingly. Let's change the amplitude of capital A and see what happens. Meanwhile, each lowercase f represents the frequency, or pitch, of each wave. Let's see what happens when we change the frequency of capital B.
For educational purposes, we've included a link to this demo that anyone can use at the end of this video. Finally, let's discuss resonance line width. But first, we need to understand resonance. Resonance is a phenomenon that occurs when an object vibrates at its natural frequency, amplifying the sound and creating a sustained pitch. This can happen in musical instruments such as a guitar string or a drumhead, as well as in everyday objects like a wine glass. In the context of sound and resonance, line width refers to the width of the peak in the frequency spectrum. A narrow line width indicates that the sound is very focused at the natural frequency, while a broader line width suggests that there are other frequencies present in the sound. This can be calculated by using the full width at half maximum FWHM approach. FWHM measures the width of the peak at the point where its amplitude is half of the maximum amplitude, or 3 decibels away. The line width is important because it provides information about the quality of the resonance. A narrower line width corresponds to a purer sound, meaning that there are fewer extraneous frequencies, while a broader line width indicates a sound with more overtone interference. Seeing that we were testing in the context of this specific experiment, resonance line width is particularly helpful, as it helps us determine whether or not sound is actually becoming purer or less complicated as we go from one harmonic to another. So what do we hope to demonstrate in this experiment? We hope to illustrate the difference between the fundamental frequency and higher harmonics, namely that higher harmonics will have resonance lines that are narrower by a certain factor at each harmonic, which will approach zero asymptotically. We believe that this works because the margin of error for sounding a harmonic must decrease as the wavelength decreases. Let's say that the node of the second harmonic can be up to 1 centimeter off from the central point, and still allow the second harmonic to sound. The wavelengths of higher harmonics will get smaller and smaller, and eventually they will be smaller than 1 centimeter. At that point, it does not make sense for the margin of error to be 1 centimeter. The margin of error should, in theory, also decrease in proportion to the wavelength, the same way that frequency increases in proportion to the wavelength. So now let's cover the procedures of the experiment. First, our volunteer violinist will get comfy in a quiet spot. We'll set up a microphone half a meter away and make sure the violin is about 0.7 meters off the ground. The violinist will play the G string and will record 20 audio samples. 10 at the fundamental frequency, around 196 Hz, and 10 at the second harmonic, 392 Hz. Next, we'll move those recordings to a computer and open them in Audacity. We'll label each one, then trim the audio to isolate the most pitch-consistent parts. We'll save these trimmed samples as new files. Now for the fun part. We'll use Audacity's Fourier transform tools to analyze the frequency spectrum of each sample. Once the graphs have been obtained, it is possible to find the resonance line widths of notable internal harmonics. In this case, we focused on all harmonics up until the fourth. We found that there was no correlation between the width of the resonance line and the harmonic played. However, seeing that audio samples were only taken for the fundamental frequency and the second harmonic, we believe that more audio samples from higher harmonics are required to discern as to whether a correlation is actually present. The first harmonic had some peaks that were not present in the second harmonic, namely the third and fifth internal harmonics. This is particularly interesting due to the unknown nature of why the peaks disappeared and should be investigated further. In short, more harmonics need to be analyzed in order to draw meaningful conclusions. This would provide enough data to demonstrate whether a trend exists, and may also provide insight into the lack of certain peaks in presumably even-number harmonics. Another factor to consider would be our software, which was very sensitive. While we tried to make our background as quiet as possible, there may have been other noises that interfered with our data. So, let's quickly recap. Some key takeaways include understanding standing waves, harmonics, and resonance line width, as well as applying Fourier transforms in analyzing sound patterns. Students seeking to do this experiment can consider additional harmonics and instruments.